A motorboat maintains a constant speed of 9 miles per hour relative to the water. The boat makes a trip upstream in 42 minutes, and the return trip takes 12 minutes. What is the speed of the current? Since we're discussing distance, rate, and time, we are going to be using this distance is equal to rate times time formula. And when we use distance is equal to rate times time, the units of the rate, which in this case are miles per hour, have to coincide with the units of the time. So we would need to measure our time in hours in order for these two quantities to multiply together to give us a distance in miles. So the first thing we're going to have to do is to convert 42 minutes and 12 minutes into hours. So in order to do that, let's take our 42 minutes and drop a 1 underneath it because we're going to be multiplying this by a fraction that is equivalent to 1. I'll often refer to this as a well-chosen 1 because obviously 42 minutes times 1 is still going to be equal to 42 minutes, but if we choose that one carefully and instead multiply by a fraction that's equal to 1, this will help us to convert our units. Now, the fraction that is equal to 1 needs to be arranged such that the units I want to cancel out, which in this case are minutes, are going to be in the denominator here so that they cancel with the minutes in the numerator, and the units that I want to convert into would then be located in the numerator of our well-chosen 1. So now that we have our units positioned correctly so that we get the cancellation that we want, let's fill this fraction in with the numbers that make this quantity equal to 1, or that the amount of time that passes in the top is the same as the time in the bottom, which means that we would have 1 hour and 60 minutes here. This is now the same measure of time in the top and the bottom, and so this ratio is equal to 1. But it's a well-chosen 1 because it also gives me the cancellation that we were after, and this fraction is then equal to 42 over 60, and the units that remain are hours from the top of the fraction back here. And so when we divide, we see that 42 divided by 60 is 0.7 hours. So now let's do this again for 12 minutes. So we write down our time, 12 minutes over 1, and now we multiply by a fraction that is equal to 1, and again we'll refer to this as a well-chosen 1. Again, we're going to want our minutes to be located at the bottom so that they cancel with the minutes in the top. And we want the units that we're trying to convert into in the top of the fraction. Then, once we have our units placed, we'll input the numbers that make this fraction equal to 1. There are 60 minutes in 1 hour, and so this ratio is equal to 1. Now we'll cancel the minutes that we were trying to get rid of. And now let's multiply to get 12 over 60, and the only units that remain are the hours. When we divide this, we get 1/5 or 0.2 hours, and these are the two measures of time that we're going to use in this problem. Again, because our rate was given in miles per hour, we needed to get our time also measured in hours. Now it's time to use our 2x3 box in order to organize the given information that will help us then create an equation that we can solve. Anytime we have a uniform motion problem, our row headers are going to be trip 1, trip 2, or in this case we can actually do a little bit better than that because we are a boat traveling upstream and downstream. The more detail we can input into this box, the better. So we'll label these rows with upstream and downstream. In a uniform motion problem, we're going to be using this distance is equal to rate times time formula as our column headers, but we want to arrange it in such a way that the first two columns multiply together to give us the third, so our column headers are going to be rate times time is equal to distance. Since we just calculated these times in hours, let's use those in our table first. It took us longer to travel upstream, and it says here in the problem upstream took 42 minutes. So 0.7 hours is what's going to go in the upstream time slot, and 0.2 hours is going to go in the downstream time slot. And now let's take a look at these rates. Up here in the problem, we see that the motorboat maintains a constant speed of 9 miles per hour relative to the water. So let's take a moment and remind ourselves exactly what that means, relative to the water. And I like to use concept drawings here in order to understand this idea. So if we have the surface of the water here with a boat that's traveling upstream and then returning, we've been given that the boat speed is 9 miles per hour. The speed of the current is what we've been asked to find. And so we're going to let that current speed be our unknown quantity, which is x. When we talk about the speed relative to the water, that basically means how fast the boat would be going if there were no current. For example, how fast it would be going if it were on a still lake. However, the true speed of the boat, or the speed that the boat is actually traveling, is referred to as the ground speed, or how fast the boat is actually moving over the ground. And this true speed or ground speed is what we want as the rate in our table. Now in this concept drawing, our boat is traveling downstream because it's traveling in the same direction as the current. And the downstream rate is going to be the speed of the boat plus the speed of the current. The current is making that boat go faster. However, if the boat were traveling upstream, which means against the current, then the true speed or the ground speed of our boat would have to be 9, the speed of the boat, minus the speed of the current. The current is slowing the boat down. Notice that this is 9 minus x and not x minus 9 because the boat does need to be traveling faster than the current in order to be able to return back to where it started. So these are the two values that we're going to plug in for the rate, essentially the ground speed, back in our table. So when we traveled upstream or against the current, our rate was 9 minus x, and when we traveled downstream with the current, our rate was 9 plus x. Now that we have two columns populated, this is when we want to multiply across in order to determine the third column. Remember, in order to get distance, we multiply rate times time, so that's going to be 0.7 times 9 minus x, and here we'll have 0.2 times 9 plus x. And now that all the cells are filled, it's time to create an equation. And what we know is that the distance that we traveled upstream has to be equal to the distance that we traveled downstream. The boat went up to a certain point, and then it came right back to where it started. So the distance we traveled upstream is 0.7 times 9 minus x, and that has to be equal to the distance that we traveled downstream, which is 0.2 times 9 plus x. And now all we have to do is solve this linear equation. So we'll begin by distributing 0.7 into the parentheses to get 6.3 minus 0.7x is equal to, distributing 0.2 into the parentheses, we'll get 1.8 plus 0.2x. Now we'll get our variable terms to one side by adding 0.7x to both sides, and our constant terms to the other side by subtracting 1.8 from both sides, so that we now have 6.3 minus 1.8, which is 4.5, is equal to 0.7x plus 0.2x is 0.9x. Now we divide both sides by 0.9. To get that, x is equal to 5. Now recall that the x was the speed of the current, and so our x needs to be measured in miles per hour. So the speed of the current was 5 miles per hour.